Good morning friends, and in this video I am going to discuss about two important name reactions, that is Bamford-Stevens reaction and Shapiro reaction. Both are olefination reaction, and in both reactions you get alkene starting from a tosyl hydrogen, and both uses base. But the type of bases used in these two reactions are different. The Bamford-Stevens reaction, as you can, so these are the two reactions you can see. This is tosyl hydrogen, and when you react it with base, you will get this alkene. Now, this base used is different for the two reaction. In case of Bamford-Stevens reaction, the basic conditions are mild basic condition like sodium methoxide, sodium hydride, sodamide, this. But in case of your Shapiro reaction, the bases are very strong, like alkali lithium or magnesium reagent, that is Grignard reagent. Okay, now we will discuss because the basic conditions are different, the type of base are different, the outcome of the two reactions are also different. In case of Bamford-Stevens reaction, you use weak base, and that's why you get more substituted thermodynamically more stable product, whereas in case of Shapiro reaction, as you use a strong base, you get kinetically more favorable less substituted product, and when I will discuss the uh, examples, it will be more clear. So what is the mechanism of your Bamford-Stevens reaction? So first of all, I will discuss about Bamford-Stevens reaction. You can see, let's say this is your starting material and use sodium methoxide base. So in this molecule, the most acidic hydrogen is this, because it is directly linked to a heteroatom, and that's why it will take this hydrogen, and you will be left with this Ts minus, and now this R, here another R. Now you can see, although it is, this hydrogen is also slightly acidic, but the basic condition used in this case is sodium methoxide. So this is not it is not basic enough to deprotonate this hydrogen in the presence of negative charge here. So that's why this negative charge will push here, because there is no chance of deprotonation. It can play a resonance between these centers, and now this negative charge can push here, and this double bond will come here, so you will get N double bond N here Ts, and here you have a negative charge, here you have R. Okay, now what can happen, this lone pair can push and this tosyl group will go away, so you will get this R, R, here you have N, here you have a positive charge, and here you have R, a negative charge. Now this is an intermediate in your Bamford-Stevens reaction, and Bamford-Stevens reaction can be done in protic solvent or in aprotic solvent. So if you do the reaction in protic solvent like methanol, if you use sodium methoxide in methanol, then methanol is a protic solvent. So in protic solvent, what will happen? This negative charge will be protonated. That is, you will get this N plus, here you have H, R, and R, here you have another R. So now only one option left to it is this nitrogen will go away as N2, because it's a stable nitrogen gas, and then you will have a cation here. Now this hydrogen can undergo elimination reaction to give you this. Okay, so this is the case of protic solvent. Now let's say the reaction is taking place in aprotic solvent. So in aprotic solvent, you don't have a proton for protonation of this negative charge. So then what can happen, it can just leave left behind a carbene. So in case of aprotic solvent, you will get a carbene and here nitrogen goes. So then what can happen, this hydride can migrate here, and this so actually if it is a conserved step, but I am showing you by breaking the step. So if this hydride will migrate here, then what will be the case, here we will have positive charge and here you will have negative charge plus this R, and of course this hydrogen. Then this negative charge go here and you will get this. So both cases you get the alkene, but you can say in one case it goes through a carbocation intermediate, in other case it goes through a carbene intermediate. So this is the difference, and this is a mechanism of Bamford-Stevens reaction. Now what will be the mechanism for Shapiro reaction? So for Shapiro reaction, I will take a specific example like this. Let's say I take this example, NHTS. So first, in this case, you use alkyl lithium. So first step, it will deprotonate this to give you this NTS minus. Okay. Now you can see these alkyl lithium bases are very strong base, so it can deprotonate another center from this negatively charged species, which was not possible for Bamford-Stevens reaction. So it can either deprotonate this or it can deprotonate this, and from that you will get two different kind of intermediate. One case you will get here negative charge and here NTS minus, and in other case you will have here negative charge NTS minus. So if you compare the stability of these two carbon, and obviously this will be more stable because it is less substituted anion, and this negative charge is unstable because this extra methyl group push electron to make it unstable. So obviously this will be major, and out of this you will get, so if this negative charge push here, this double bond will migrate here, and this will in turn kick off this tosyl. So you will get this N, this one, and here you have N double bond, also a negative charge. Now this negative charge come back and it will put a negative charge on your alkene. So here you will have a negative charge, and from this particular case same thing will occur and you will get a negative charge here. Now these two are the intermediate for your Shapiro reaction, and what they can do. So in if you apply only workup, acidic workup with H2O plus, you will end up getting a simple alkene, but lot more can be done. You can use any electrophile, let's say RX, any electrophile, so that can add to here. So R can add here. So this is a functionalization, and in this case also you can add Rx and you will get here R. So two different products can be obtained. The radio selectivity is different, but in this particular case this is 98% and it is only 2%. So you can see most acidic proton is deprotonated in case of Shapiro reaction, and that's why you get regioselectively the less substituted product, because in this case you use the strong base. Another important reaction which also came in CSIR exam, yeah, from Shapiro reaction is this one. So here you have a carbonyl group. this carbonyl group is first made this tosyl hydrazone, and then it is reacted with say R mgx. So what will be the case? You will get, if you draw the full mechanism, you will get uh, this n minus, right? No, n minus, it is right. Then you will, so first of all this deprotonation and this tosyl. Now you can see there are two hydrogen, this one and this one, but you know that in bridgehead you cannot form double bond, so this hydrogen cannot be eliminated. Instead you can deprotonate this one, so R minus will deprotonate this, and so actually I did a mistake here. You should have this. Okay, so now this double bond will go here and it will go again, so you will be getting this n minus, and now when it come back you will get this negative charge. So in, then if you have any electrophile present, let's say Rx, this position can be proton alkylated. So this is example which came in CSIR exam, and there are lot of other examples you can practice, but this is the mechanism of this Shapiro reaction. And as I told earlier that the regioselectivity of the two reactions are different. In Bamford-Stevens case, you get more substituted double bond, that is thermodynamically more stable product because you use weak base. But in case of Shapiro reaction, you get kinetically favorable less substituted product. So that's all. Thank you for watching, and subscribe my channel. Best of luck.